for the second day. Let me summarize what we have done during the first day. So we have started with introduction to 3D printing technology. So where we have discussed why 3D printing is needed under Industry 4.0 and when do you need this, the differences between the traditional manufacturing systems and additive manufacturing systems. And we have talked with a design for the 3D printing and then 3D printing processes, a glimpse of 3D printing process, applications, general applications, COVID-19 applications, futuristic applications. And then finally, what is the future of this technology? So that's what we have discussed during the session 1. And during the session 2, we have Professor Krishnanand has given the introduction to CAD systems. So where we can use, say, surface modeling, wireframe modeling, solid modeling, and that is basically a parametric modeling systems. And of course, BREP and CSG kind of representation schemes he discussed. And then how to convert your CAD models into STL file and what are the problems with the STL file, and of course advantages of the STL file, and then the new file format called AMF, which is developed by ASTM committee, F42 committee. So that's what so far during the first day, that is session 1 and session 2. In a summary, we have discussed those concepts. Now, second day, that is today, the first session means that is the third session of the workshop. So that is on 3D printing design process and software. So I'm going to cover these topics during this third session, that is introduction to 3D printing design, 3D model capture tools, in a recap, yesterday what we concluded is for 3D printing, we need to have a digital model in order to fabricate any component or any product or any assembly. So we need to have a digital copy of that product. So then how to get digital CAD model or in general STL file, how to get, in how many ways you are going to get this STL file. So first one, I'm going to talk the interface to the 3D printing software is either you can interface the data or either you can get the STL file through 3D model capture tools. Means basically it is through scanning technology. Means You have a physical object. We want to get a digital copy of it. So during that situation, so then you can go with this 3D model capture tools to get the STL file from the physical objects. And second one is CAD design tools. So we are very much familiar about these CAD design tools, that is CAD/CAM CAE softwares to model the component by using any CAD/CAM CAE software. So that is the second kind of interface we can give it to the 3D printer. Or third one is repository kind of tools. So what do you mean by a repository? So repository is a, a digital library basically, which it consists of hundreds or millions of models in terms of STL or in terms of .prt or in terms of .part or any native format of the CAD/CAM CAE softwares. So that will be kept in a centralized place or called a library, digital library, or online community, whatever you call, or a repository kind of interface. Means already somebody has modeled and it has kept in a digital library. So that is the meaning of a repository kind of tools. You have a plenty of digital libraries or online communities available. You can download without drawing or without making a model. So you can go to the website or go to the digital library and you can download. That is a repository kind of tools that we are going to talk about those tools. And you have a fourth interface to the 3D printing systems is medical image processing tools. Means from the medical data, means either CT, MRI, ultrasound, PET, angiogram, or even a digital X-ray. So then how to convert those medical images into STL file. So that also we are going to cover. That is the fourth interface to the 3D printing softwares. And once you have created by using any one of these four methods or interfaces, you are going to get an STL file from these four platforms or four different areas. So then once you get that STL file, so mesh repair and slicer tools. What do you mean by this? So during session 2, we have learned that there are a lot of problems with the STL file formats. Say you have triangles which are missed or misplaced, or normals are got flipped, or triangles got overlapped. So many, or some kind of degeneracy towards geometry or towards topology. So you have several issues with the STL files. So then how to correct them? So in order to correct them, so as we know that STL is basically a mesh file. It is not a 3D surface, neither nor a 3D model. Basically, it is a mesh based file. It's a mesh file. So then how to repair your mesh, your triangular mesh? So you have some softwares or some tools available for doing that mesh repairing. And then finally, we need to slice, being a additive manufacturing, we need to take this model and we need to slice into layers. So in order to do that, we need to have some slicer tools. So then we are going to see some of the slicer tools. So I'm going to put proprietary softwares as well open source softwares also under these 5 domains. And then finally, Design for additive manufacturing. What do you mean by design for additive manufacturing? So normally, design for manufacturing, but this is designed for additive manufacturing. What do you mean by that? That also we will see during this session. And then how do you control the process, and how do you control the quality of the 3D printed parts? So that these are the very challenging nowadays. So how to maintain the quality, how to maintain the repeatability, how to maintain the consistency of the parts. So that is vital nowadays. So then we will touch up some of the concepts in that domain also. And finally, what are the various 3D printing services across the globe? Who is offering? That also we are going to see. And with that, we'll conclude this session. So this is a brief overview of this session. So then, what is 3D printing design process is consists of what? So as we discussed previously, so then you have a 3D model capture is the one interface. So you have some softwares, or you have some 3D scanning devices to capture the data. So means from physical to digital, you are going to use some kind of softwares like Kinet Fusion or Autodesk Recap. So you have some softwares, and along with the 3D scanner hardware, so we are able to generate an STL file. So our aim is to generate an STL file or a OBJ file or a AMF file or a 3MF file. We'll see what are these files. You have already exposed to STL and AMF, and we'll see the other two file formats also during this session. And you have one more interface or getting the STL file is a CAD design or a CAD CAM CAE softwares. So which majority of the people may be using this kind of tool. So you may use some softwares like a Blender or Fusion 360 or Meshmaker, Reno, Katia, Proe. You have a good number of softwares under this CAD design domain. So from this platform also you will get, or you can generate an STL file. And once you generate, otherwise even you can include the medical imaging also here, so which we discussed earlier. So you can use any or even a repository kind of interface where you have a digital library which you can download the STL file directly from the open communities. So once you get this, so we need to repair the STL file, or we need to correct the STL file. Sometimes, need not be every time. So then in order to do a repair or a correction, so you have some softwares under this mesh repair softwares. You have a NetFab, and you have a AD mesh mixer, and you have a mesh lab, and so on and so forth. Magix. You have several softwares under this, and we are going to see both proprietary as well as open source softwares under this mesh repair also. And then finally we need to slice them. So we need to have a slicer software like Cura, and we are going to have a repeater or a simplify 3D slicer. You have a several open source, almost all these are open source softwares, that is for FDM process. So you have these slicer softwares that also we are going to discuss. So is there then what is the difference between the traditional CAD modeling and 3D printing design? Is there any difference? Yes, there will be a difference. As we already discussed, the STL file is the mesh file, right? Mesh file, it will be having its own disadvantages or limitations. So then we need to have other softwares also. Just now we are discussing. So like traditional, even you may be transferring the data from one platform to other platform. Like normally what you do, you may use for modeling, you may use one software, and for analysis you may use some other software, and for simulation you may use some other software. Similarly in AM also, you don't have a single software to accommodate all these mesh repairs or slicer software, or even a quality checks, or even a build simulations. So you don't have a single software to perform this. So you even you have some design libraries. Just now we are discussing, like you have some digital libraries of existing 3D models like Thingiverse. But anyway, you are going to have a lab session. During that lab session, you are going to work on this Thingiverse, and you are going to work on GrabCAD also. These are the two online repositories. It doesn't require any exe file to download in your this is basically a browser-based kind of a website. So you can download. We are going to give the exercise also on these two softwares. Softwares are repository or design library, whatever you call. That is a GrabCAD and a Thingiverse. And anyway, that we'll discuss during the lab session. So you are going to add some colors to the, as we understood from the second session, STL file doesn't contain color, STL file doesn't contain any texture, STL file doesn't contain any material, STL doesn't contain any volume. So we need to enhance. Why? Because your printer is able to print in color, your printer is able to print in different textures, lattice structures. So then we need to enhance the STL file by maybe by using some softwares like say Blender, or a GrabCAD will be used to add some color or to the textures to the STL files. So this is in brief the workflow in the 3D printing design process. So today, entire this session, everything is towards digital or soft data we are going to talk. So I'm getting a lot of requests from the participants saying that can you cover some research topics? Yes. So doing research by using software simulations, so it is less expensive, or you do not spend much of the money. Why? Because if you want to do some experiments on the metal 3D printer, so they may be charging 4,000 rupees per hour or so. But software or developing a code, it is less expensive, or it may be with free of cost. You have all these open source softwares nowadays, so you can do without investing your money. You can complete your research, right? So this session is going to be the very good for the people who want to do research using less money or no money. You can write a code, or you can use these open source softwares for simulation, or for slicing, or for mesh repair, or for any application oriented research. So you can use these softwares. So you can concentrate, or if you want to have some specific questions, you can ask at the end of the session during question and answer session. So design and modeling. So just as a recap, Professor Krishnanand talk. So you have CAD models. Nowadays, CAD models are very beautifully represented, rendered images. Basically, it's a rendered image, right? So which we can feel like a metal spring, but it's in fact it's not a metal. Basically, it's a virtual model. It's a digital model, but how beautifully it got rendered. So appearance wise, it looks like a steel spring. Anyway, so you do model, and what is the next step? We need to convert as STL file. So this is STL file, which you can closely observe. There are some triangles on the outer surface of the model. So we need to do these two steps in any one of the CAD modeling software. So and then convert that as STL file, and then we need to do a check for any problems or any missing triangles. So then we can use some kind of repair software to do that. And then once you do checking, and once you, but why you want to do that or where you want to do that, so that is the biggest challenge here. So your CAD/CAM CAE package doesn't have any provision to check the STL file healthiness. Neither CAD software nor 3D printing interface software is not having this facility. So that is the biggest issue. Then you may look for the third party software to do correct these STL file problems or anything you want to check whether it is a watertight model or not. We need to ensure before you send it to the 3D printing interfacing software. So for giving the supports or for slicing or finally to generate the tool paths. So we need to check, even if it is a polymer machine, it may not be costing you much if some build failure has happened. But if it is a metal 3D printer, it costs you much. So then you must have some simulation and some quality checks before you fabricate on the metal 3D printer in order to save a lot of money. So just I want to uh, put some of the data file formats. STL, as we know, it's a de facto standard, and this is a bold and simple format, and which describes the object as a series of linked triangles or a tessellation, which you can see this one, and no information regarding color, texture, material, and file security. So these are the issues in STL. Then what is a .obj? So that .obj is an object file. So this will add the color. Say why you need .obj, you have STL file. So just now we discussed STL file doesn't have any color. So if you want to give the color to the STL file, then you have to have a obj file to give the color. And high precision printing, you have a very good high precision printers nowadays, so like SLA technology, which it will do beautiful precision and beautiful colors you are able to print, but your STL does not support the color. So then you have to convert as a .obj in that case. And even you want to add some material, so you have .mtl format, that is a material library format, so which apart from the color and texture, even you can add the material also through .mtl, which you can see this is then uh, from the obj, and it has given the material, and now it has become, or from the STL to MTL, so which we can add the material. So this is what, where we can enhance your STL capabilities either through OBJ or either to AMF. So AMF is developed by ASTM, and .3MF. Nowadays .3MF is also very well known, and people are adopting this .3MF, and surprisingly it is from Microsoft. So these are the four popularly used file formats in 3D printing. And then we'll talk about the 3D model capture tools, that is 3D scanning. So what is all about 3D scanning? So 3D scanning is we need to start in a physical object, the existing physical object, and use some sensors or the digitizers or a 3D scanners. So either a touch probe or a laser or a white light. So any source use. So in order to collect your model into millions of points called as a cloud data, point clouds. So first we need to touch this probe, and if you touch the probe on this surface and in the computer or in the software, so you're able to get that three-dimensional point here. So like that, if you touch on the surface, maybe hundreds or millions of points you can collect, and you approximate these points into triangles. If you join 3 points and you will get a triangle, so like that you can convert these points into triangles called as STL file, or further you can convert your triangles into a surface, a freeform surface, and further you can convert as a solid model also if required. Depends on your application. Your application is only 3D printing, you can stop it at the STL file, or your application is for FEM or CNC, then further you may go with a step file, or so whatever software interface is good for your application. Further you can process this material, this component from point cloud to the required shape. That's what, then you can use your application, either a CAE application or a CAM or even a 3D printing application, to print this model. And during this course, if you want to modify in the software, even you can modify this design and you can print, or as it is, if you want to replicate, don't modify, just you can give to the print or a CNC machine to get, or modification is also allowed. Soft to hard, hard to soft, it will be having a very good advantages. So then you have a different types of scanners. As I mentioned, you have a physical touch probing, or you have a laser beam probe, and optical CCD cameras or CT scanners. So these are some of the scanning devices or the sensors used to collect the data. And you have a different scanning systems. So basically, how do you select a scanner? So that depends on what is the size of on an object which you are going to scan. So if your scan object is 0.01 meter to 1 meter, so then you can use any one of these. So like that, if you have a bigger components like 30-meter size, or it may be 20-meter size, and for that also you have these Faro laser tracker or Renisha. You have a different, there will be a slight difference between the CMM and a scanner. Basically, CMM is good for geometrical shapes, and but scanners are good for freeform surfaces. So, and probably more or less this may be, again, you have a different scanning devices and different algorithms to reconstruct your point clouds into surfaces or further solid models. So this is a brief about the uh, the reverse engineering or so-called data capture. So then what are the different softwares that are available to do this kind of capturing the images through scanning or through digitizing? So you have a Geomagics is a one software, and you have Connect Fusion, you have Recap, and you have a Metashape, and you have a Connect Capture, and you have a Scandy Pro 3D, Scan 3D, Trino, Culo, Polyworks. So you have plenty of softwares. Even you have a drone, for drone applications also you have as exclusively software, and some of them are open source, some of them are proprietary. Among these, you have a plenty of softwares available in the market to reconstruct your point clouds into a STL file, or in general into a CAD model, or in general into a digital model. So then other interface is a CAD design. We are very good, or I hope 99 or 100% people might have used any software, for CAD modeling of your design during your research or during your teaching. So I'm sure 100% people might have used this kind of CAD modeling tools. So either it can be a two-dimensional modeling like AutoCAD, maybe using, you have plenty of softwares also, but nowadays AutoCAD, they're giving a free of cost for the educational licenses. So you have even other side, you have a solid modeling or three-dimensional modeling softwares. So nowadays making modeling in 2D or 3D is not a big deal. So you have even free of cost these software, so you can get it. So then you have, so you have so I have given a broadly into say freeform softwares or artistic softwares. Say for example, you take Blender, or if you take Lightwave or 3ds Max, Maya, Cinema 4D. So almost like this, up to this is a freeform or artistic, or for animation, you may be using these softwares, and some softwares exclusively for sculpting. Nowadays, these softwares, no, like a digital clay, you can play, no, like how you take a clay, a designer can take a clay and then he can mold as he wish. So then similarly, a digital clay kind of a stuff. So you have a sculpted kind of a digital sculpting. So you have softwares like Sculpt, and you have a ZBrush, and you have a Sculpt GL, and these are the softwares for sculpting or for a kind of no digital clay you can play. So like that is the thing. And of course you have open source softwares like Tinkercad, and you have a Google SketchUp, and you have a Reno, and you have a Mesh Maker, and you have SolidWorks, Inventor, Fusion 360, AutoCAD, Creo, CATIA, OpenSCAD, FreeCAD, and you have other softwares. So all these softwares. So, and we are going to give a demo on SolidWorks, but I'm not a sales representative of any one of the CAD software. But um, as far as SolidWorks is concerned, so it is more user friendly than any other software in general. But maybe some other softwares may be good in some other aspects. So, but which we are going to give a demo on the SolidWorks software for how to make during the lab session. So then, if you are not having a SolidWorks, you don't worry. So, and we are going to give exercises on these open source softwares also, and we are going to give a demo on open source softwares also. So this is about a free form or artistic or in general a CAD design softwares. And then we'll talk about a repository kind of a tools, like where you have a digital library or an online community, or nowadays again it's a cloud-based systems, right? So you will not save in your no local disk or no. So nowadays you have a cloud-based systems. So then this kind of a repository kind of a tools where you have a plenty of repository or the places or the websites where we can freely download these STL files, and we are going to it is not possible to cover all, but we are trying to cover two softwares at least. One is the Thingiverse, another one is the GrabCAD. So Thingiverse is for a general hobby sake, and GrabCAD is for engineering applications. And of course, you have other repository or online websites like Qt or a Free 3D, My Mini Factory, and you have a Pinshape, STL Finder, Sketchfab, Yagi, and Umagine, 3D Shock, and you have a 3D Warehouse, you have a CT Trader and Turbo Square, Zimple, Print Me a Sheep, Hum 3D, so 3D down. So I have put a very few here. So if you Google it, so you can get tons of, but the number of STL files may be varying. But if you take Thingiverse, I'm sure it may be millions of STL files you can download free of cost. And of course, GrabCAD also. So this is about the repository where you need not model it. Somebody else has already modeled, just you can download as a free of cost, go to their website and you can. So then other interface is a medical image processing tool, like where you have a CT or a MRI scan data. So, and just to give a brief, so these medical image processing nowadays, again, thanks to the PC, with the advent of PCs, the personal computers. So you have, even in a radiology or in general in medical imaging, you have a very good opportunity. You have all the images are digital now. Otherwise, you used to have only X-ray before the PC. So you used to get only the single cross section at a time, and and we used to print on a hard copy every cross section. Every time we need to waste the film to get a single cross section. But thanks to the computers, so you can get hundreds, thousands, or millions of images, and you have the computer to have a memory to store this and to analyze. And of course, you have a MRI, so you have a CT data, you have a MRI data, and your region of interest is bone. Then definitely your radiologist may advise to ask you to undergo a CT examination, and your region of interest is a soft tissue, then you may be advised to undergo MRI and things like that. You have ultrasound, you have a PET, and depending on region of interest or the tissue of interest, so then you may be asked to undergo different image processing techniques. But either in general it may be a CT or a MRI, so then you are going to get these 2D cross sections. But we need to have some medical image processing software to give a life to these black and white images into color, or in specific some material or some bone density, right, or some tissue, or some neurovascular structures, so or some ribs, or you see. So from the black and white images, so even I can give a life, or you can give, say I can segregate, I need to have only the ribs. For one point of time we need to study only the rib, or other point of time we need to study the lungs. So we need to study the lungs more now. Why? Because of COVID-19. So then you have to secure your lungs. So then we need to, you have an opportunity of, in terms of medical image processing software, you can supplement your black and white images, or you can give life to the black and white images to a virtual model like this. So then how to do it? So you may have several medical image processing softwares. So you can create an interface, or from CT, MRI to CAD model, you can, or you can simulate, a surgeon can simulate his surgery, or even you can design some implant and check for the fitment, or that validations, so you can do. Or further, an orthopedician has designed some bone and he wants to test whether it is withstanding the loads which a normal bone withstand, but whether the implant is withstanding on par with the bone. So you have a FEM analysis, and we can do that FEM analysis from taking a bone data of a patient. And of course, you can make a physical 3D models and design verifications. You can do several things once you have a medical image processing software with you. So to name a few, so these are the medical imaging processing softwares. So almost from the left, yeah, it's a mix of open source and proprietary. But Mimix is a proprietary software, and you have iNutrition and a Fast, and you have a Dolphin 3D Surgery and D2P, Amira. You have Oris MD, Viteria, and 3D Doctor, Simpleware, and people may be looking for a open source software. The open source software is 3D Slicer, so you do not pay anything towards this software, and capabilities almost equivalent like a Mimix or 3D Doctor or a Simpleware. Simpleware is also a proprietary or a paid software, but it is not as costly as Mimix. But you have maybe different capabilities of individual softwares, and it may have its uh, different capabilities and features and advantages, disadvantages. So to list a few, these are the medical image processing softwares for 3D printing. And then we'll talk about a bit on mesh repair and the slicer tools. So mesh repair, so in order to correct your STL files, so then we need to, or you want to add some text onto them, or you want to measure. Why? Because why you want to measure, you may get doubt why you want to measure. So in the software you can measure, right? So but at the moment you saved STL file in your software like SolidWorks or any CAD modeling software, you cannot touch, you cannot edit the STL file in any one of the none of the CAD modeling software will allow you to edit the STL file. Again, you have to go to a native format of that particular software, and then we need to edit, or even we need to measure the dimensions. But that's what the third party software is now in between. So it will allow you to do this. Then why you want to do this? Say you are running some service bureau and your customer has sent some STL file to you, and design for additive manufacturing is another concept here. So then you have to make your design to ready for the 3D printer or additive manufacturing. During that course, you may require to alter the CAD designs. So then it is not advisable. No, again, sending back to the customer saying that, hey, can you do this? So that is not a good idea. So if you have some third party software like this, so then without asking, or without, or through phone, you can even any modifications, or say whatever the surface finish is expecting, so something like that. So you can even all these stuff on STL file I'm talking about. So then you can do a such kind of visualization, measuring, labeling, painting. Why? Because your printer is able to print in color, but your STL file is black and white, remember. So then we need to give some colors, and we need to make it a halo, means we want to reduce the weight of a component. So you want to not solid I want to make, and so I can make as a halo, so I can save a lot of material. So then I can use some Boolean operation here. So then I can smooth in the STL file. Say probably it might have scanned, or so due to scanning you may have some noise. So then we need to smooth in it as it is. So here you know the concept of garbage in, garbage out, right? So if you give garbage to the 3D printer, so it will give you the garbage out only, right? So then we need to give a very good quality STL file to the printer. So then only it's going to replicate almost to the quality. So whatever the original quality you're going to get. But if your source file itself it's a bad, or the surface is not good, so it's going to replicate same. So then you may use some kind of visualization, some kind of flipping the triangles, as Professor Krishnanand was yesterday talking about this flipping of the normals or flipping of the triangles. So, and of course, we have some automatic stitching options also. So I'm not a representative of any one of the software, please remember. So these can be done in any mesh repair software. Nowadays you have open source softwares also. I have listed at the next slide, so you can note it down, some open source softwares also. We need not buy these costly softwares nowadays. So you can have an automatic stitching option, and you can have some automatic triangulation. So you can have some manual repairs also, it will allow you to do. So of course you have some support structure. We'll see slowly, we'll come to the design for additive manufacturing. In that, supports are the main criteria, like where you can combinedly make with the model and support. So then, so instead of giving a same pattern to the model and support, anyway support is just for giving a support, or just like a scaffold. It is giving for ease of fabrication, for time being you are giving some strength to the model without falling. So then you are going to remove that once it is printed. So then you can vary the type of support, so based on the feature. So if you want to give a support to the larger surface, then go with the block kind of surface like this. And you have the surface is very narrow and very thin. Like say you have this where you want to give some support here, very narrow and thin, and then go with some kind of a line support. And you have some portion where very small feature here, so then you can use some point support like this. And you have some overhang here. So for the overhang kind of a portions, you have some cassette kind of a support. And you have some circular feature where we need to give some support to that circular feature. So then you can use a web kind of a support. So like this. So depending on your surface geometry, so then you can vary the support style. So and then we'll move on to the slicer software. So what exactly a slicer software will do? So we have to start your CAD, or in general your now no more CAD. Why? Because you have other interfaces also. Just now we have seen medical, and we have seen scanning, and you have a gaming data also nowadays. So you can source your data from any areas, and you bring it as a .stl or obj or even x3d or 3mf or amf or any format, and then you need to slice this. So that slicing will be done, say, Cura. Cura is one software. It's an open source software which is developed by the Ultimaker. It's a Netherlands company. So they developed this software and they kept open. It will work for any FDM process, any FDM printer, and even your DIY printer also. It will support. You can use it, this Cura software for slicing. So as we know that once get this STL file, and then we need to slice it, and in order to generate the G code. So the G code will be generated through this Cura software by giving the layer thickness. Say, hey, I want to slice with 0.1 mm or a 0.2 mm or a 0.3 mm. So just you specify what is your layer thickness, and it's going to digitally slice it, and it will generate a G code, and you send that G code to the printer. So where it's going to happen here, the physical realization of this same G code. So you have sent this, say, first layer. So you send this first layer here. So from bottom up approach, and some printers may be top down, and majority of the printers may be from bottom up approach only it will follow. Some latest printers in some domains like DLP and some other areas, like where it may be from top down also, but 99% of the printers are from bottom up approach. So it will go from bottom to top. And what a slicer. So this is the G code. You are very much familiar about a CNC domain where you'll get a G code. So it is a similar G code it's going to generate. But you are not writing, it's automatically generating. So your Cura is automatically giving output as a dot G code, giving input as maybe anyone or maybe STL in particular. So depends like what kind of interface which you have with that. And then slicer, which creates a toolpath, and more or less it may be intelligent based on your geometry of the design file, and a percentage of infill. So of course you can vary the density. That is the unique advantage of additive, in contrast with a subtractive process, where I can make this as 100% dense, or even I can make 80% dense, or even I can make only 10% dense. So I have a flexibility here. So then you can make changing the infill density, and even you can support structure. And if the geometry is difficult to print, then it may require some supports. So of course we'll see in the upcoming slides about these support structures and how to generate and different kinds of support structures. And you may have other softwares also. You have repeater, slice 3R, and Cura and Simplify 3D. So these are the two very good softwares. Why? Because I have used both. That's what I'm telling. So you have other softwares, maybe all are open source here, whatever listed here. So you have a 3D printer. So to name a few, so up to Magix, the softwares, or STL repair softwares. From Cura, all these are slicer softwares. So you have STL repair software like 3D printer OS. You have a 3D tool free viewer, make printable, mesh mixer, mesh lab, mesh fix, netfab, magix. Up to this are the STL file repairs. Some of them are majority of them are open source, but Magix is a proprietary software from Materialize Belgium. And you have a Cura, Simplify 3D. All these are open source. Almost all these are open source softwares. You can download free of cost. This is for a slicer software, so which it may be having a slice engine inside to get the toolpaths or to get the G codes. And then we'll talk about design for additive manufacturing. What do you mean by design for additive manufacturing? So design for additive manufacturing is all about how you can make your design ready to print. So what do you mean by this statement? Say, why can't a conventional CAD model which you might have designed in a software like CATIA or SolidWorks, we can give as it is, right? So then why you need a separate design, or why we are taking a third session exclusively on design for 3D printing or design for additive manufacturing? Why you want to do this? Definitely 3D printing it's a disruptive technology. It is not similar with the traditional manufacturing practices or the fabrications like machining or a tool making. No. So your CAD/CAM CAE softwares might have tuned to the conventional manufacturing systems. It might have tuned to that. Like you have a parametric design, you have a generative design. Now people are talking about, but why AM is looking for a different design, or why it is unique, or why it should be different from CAD/CAM CAE software? So that is the thing. Say, as I already introduced, supports is the one thing, and you may have some flexibility, and at the same time you may have some limitations, or you may have some constraints. So then only we need to talk about a design for additive manufacturing. Otherwise, you can directly take this. Just now whatever so far we discussed is, so you need to have some CAD model and convert as a STL file and send it to the printer. So we are seeing only one side of the coin, but how to generate a design, how to fix up a orientation. So sometimes too much of flexibility is also leading to some difficulties or some challenges. Too much flexibility is also, no. But anyway, under this design for additive manufacturing, let us talk. We'll take the first most important parameter is a part orientation. So what do you mean by a part orientation? Say, why you are separately talking about the orientation? In the CAD software itself, you might have oriented with some orientation, but then why you need to separately talk about the part orientation here? Why can't it be your design part orientation, which you might have designed in your any one of the CAD/CAM CAE softwares? You can as it is replicate, as it is you can use that orientation. Why you want to change the orientation? Definitely orientation is changing all the spheres of your requirements, or quality, or cost. It is affecting your quality of the part, cost of the part, whatnot, and time also. Basically these are the three things, right? And of course mechanical properties. In general, quality you talk about, so it is judging your quality, and it's judging your speed. So say you have different criteria. This is a very big subject to discuss, but anyway, in a crisp, so your part orientation, so you may have, so by thumb rule, better you select a orientation which is having a minimum Z height. And the quality, obviously you have to choose an orientation which should give better quality, of course. And the area with the base of your support should be good. Then you choose that kind of, these are some of the thumb rules or criterions, whatever you call. The mechanical properties of the part produced should be good. You may not get the same mechanical property if you orient one in one orientation and you change the orientation angle. You cannot, that is the limitation or a drawback or whatever you call. So you cannot get the same mechanical property if you orient with 0 degrees and you have one more sample with 90 degrees, and if you compare the mechanical property, it never match. Any of the 3D printing technology out among any 7 if you take, so it will give you a different mechanical property of each sample. Anyway, so use of external support structure, you try to minimize the external support in such a way that you can choose that orientation. Say for example, this is your design orientation in any one of the CAD modeling software. So as we discussed the previous slide, so you have a 5 criterions. So you choose which criterion. So again how to, and then your artificial intelligence or a kind of data analysis or whatever you call, like expert system. So somebody is asking, sir, what we are going to do in the research. So then you can develop some artificial intelligence algorithm to set which criterion, or you combined all these objective functions and you make a multi-objective function to optimize your part orientation, right? So you can do it as a research, right? So part orientation. And of course, if you talk about the surface finish again, say for example, for a given same layer thickness x. So if you compare for a given same layer thickness x, and if your orientation is, say for example, approximately 45 degrees, so then what could be the error? So this is the error. Why? Because this is the staircase effect. You know what is basically 3D printing? It will print layer by layer, right? So means either it is a straight line or a curve. Ultimately, it is going to represent with a step kind of a layer, right? So it's going to layer by layer, like brick by brick, it is going to build. So your angle is a major thing here to judge your surface finish. So if the angle is more, which you can see, the deviation is less. But if the angle is less, your deviation is more. So if you take the combined or cumulative effect of this error, so it may be more here than this. So your orientation is affecting your accuracy or surface finish, right? So which we need to and then mechanical strength. So if you make one sample in 0 orientation and you make other sample in 90-degree orientation, so and you see the fracture, the fracture mechanics of this sample and the fracture mechanics of this sample, it's totally different. So means the mechanical strength is different with 0 degrees orientation of your sample and say 90-degree orientation of the sample. So it is judging your strength. And then somebody was asking, sir, can you include some cost analysis? But anyway, the Rakesh is going to talk elaborately on, he's an industry person, which he can give more insight on the quotation or cost. How do you arrive the cost for build? I'm talking about per piece cost. So, but in general, how to calculate the total cost? So the total cost involves, so your pre-processing cost. What do you mean by pre-processing cost? Whatever we are discussing during this session, everything is a pre-processing, means design. That is in the software. So pre-processing cost, and of course build cost, that is utilization of the material. So your machine rate and that thing we need to consider. And of course material cost, which we have to add to the rest. And finally the post processing cost. This is vital nowadays. So in order to minimize the post processing, your design for additive manufacturing has to give less supports, right, and easily separate from the substrate, things like that. So what I'm trying to say, in 3D printing, software is magic, but not the hardware. So you remember, so design for additive manufacturing is a magic, but it is not the hardware. Hardware is a slave, as you know that. So as for the G code, so it will work. So then I put some literature, but somebody has asked, sir, can you have some research problems? But it may be bit old research. The different researchers, in fact, during my MTech, I used to refer these literature survey, but nowadays I am not finding this kind of literature towards slicing algorithms. But this is one slicing algorithms to fix the orientation by taking the surface quality improvement. So maybe area into perimeter, and you have different people have come out with different criterions. Maybe your angle is playing a vital role, and your cusp height is the one where it's a deviation from your CAD model to the layer. So this gap called as a cusp height, and you have this angle, orientation angle. So then you have some mathematical, people has developed some mathematical models. So you can refer some of the literature, but nowadays there is not much in the focus of this. Why? Because you have a open source softwares, right? So, and even nowadays all these softwares, they may be having an artificial intelligence kind of stuff, right? And you have a blockchain also for security, that also we'll discuss in the upcoming slides. So anyway, so we need to have some kind of criterion or some kind of people. You can develop your own mathematical algorithm how to improve the surface finish. Why? Because you cannot eliminate the staircase effect. Why? Because this is by nature, layer by layer it has to lay, but you cannot change the approach. So means what you can do is you can minimize these errors, maybe here. So what you can do is you can minimize all these errors, but you cannot eliminate the errors. But how to minimize those errors? So then you can calculate each layer what is the deviation, and you find out the cumulated error of this stuff, and you can come out with a kind of a new algorithm or a new method of approach to optimize these surface or the quality improvement of these models. So during slicing or during fixing the orientation, or you can integrate all these factors. So one may be, so all these are again interconnected, right? Just now we are talking about part orientation, and we are talking about support, quality. So all these are interlinked parameters. So then your part orientation must give a minimum support. So anyway, support is a support, it's a waste, but it is needed wherever you have some overhangs. And of course we need to start with laying some support material on the substrate or on the plate in order to overcome the damage of your part. So if you start with first layer on the platform, so while peeling your part, and you may damage your surface of the part, then you put some raft. If you talk about FDM, it may be raft, the terminology may be different. If you go with metal printer, so it may be something else, but FDM in general, you may talk about some raft. So you start with putting some layers with the support, the kind of a raft kind of a support. You put some 5-6 layers. So that depends, you can customize also, but just you give some kind of a support for the on the platform that is needed. And wherever you have overhangs like this, and angle also, so this slice, it doesn't require any support here, but here you may require, right? So like that, wherever you have a projection or a overhang, then we need to give the support. So then, so if you orient to 90 degrees, then your supports are totally different. It may be more supports it may require. So then so support is also, while calculating the cost, the support material is also as equal to the model material. So then it will become more costlier, not only costlier, so it may double your build speed. The speed also less, because we need to lay both model as well support. So then you try to minimize these supports, say by fixing your orientation. So then maybe some thumb rules will be given in order to, or some multi-criterion objective functions you can derive to optimize your part orientation. Say you ensure that you have the maximum number of perpendicular surfaces, and ensure that you have a maximum number of up-facing horizontal surfaces, and ensure that your maximum number of holes, your the axis hole, the whole axis is there na, that should be in line with the slice direction. So this is another thumb rule. And maximize the number of curved cross sections draw in the horizontal plane. So you try it, but don't go for the vertical plane. Why? Because you have a staircase effect. But horizontal, you don't have that problem. Then you ensure that your curve surfaces as much as on the horizontal surface, but not on the vertical surface plane. And maximize the area of base, of course, base surface, and minimize the number of sloping surfaces. That is another thumb rule. And minimize as many as the overhangs, the overhang surfaces, right? And minimize the number of trapped volumes. The trapped volumes are especially for the process like vat system and powder based systems, which trapped volume is a major issue. Then again, we need to put some drain hole, and we need to leak that, we need to drain that raw material which will be there in that model. So then you try to minimize those trapped volumes. So these are some of the thumb rules where it may work for almost all the 7 processes. And again, if you do some microscopic analysis, it will vary from metal polymer printing. You have a different ball game, and the metal printing altogether, it's a different ball game. So then we need to we need to play. So then support structures, of course, support structures, but support structures may not be the mandatory for all the 7 process. So process like FDM and SLA, it requires a support structure. So process like SLS, powder based system, that is only for polymers. It doesn't require any support. The loose powder will act as a support there. So in general, so Rakesh,
సార్ చెప్పండి.
రూమ్ లాక్ చేయలేదా మీరు?
చేశాను సార్.
ఓకే,
అయితే కొంతమంది మళ్ళీ వెళ్ళిపోయారు, యాక్సెస్ చేయడానికి ఇబ్బంది అవుతుంది.
ensure that there won't be any disturbance during the presentation. So let them mute their microphones. Why they want to switch on the microphones? So they want to talk, then I will switch off my microphone, and then we will on their microphone. Let them speak.
Okay.
Thank you, Rakesh.
Okay.
So we of course 45 degrees, less than 45, maybe it may require some mandatory of the supports and things like that. And adding support structure with specialized softwares like Simplify 3D, Cura also, of course. Simplify 3D and Cura, these are the two best ongoing the open source softwares which will work for any FDM process, and more user friendly also. Anyway, you are going to work on a Cura software, and we are going to give exercises also on Cura software today. We'll see that also. So then how to which we can see there are some supports here, like where wherever you have this projection under this chin, and there is a projection which we need to give a support here, right? So we need to give a support, and these supports are given by using this open source software. So broadly we can divide the surfaces into 3 categories. So one is a separator, that is a raft that is on top of the substrate, that is called as a separator kind of a support. And you have a main support. So this one as a main support, and this support you call, and the support which is in contact with the model, that is called a sierra or a needle kind of a support. You see this light color portion, so where your support is directly contact with the model, so that is called a sierra or a needle kind of a support. So this support also, it's a different ball game for the polymer and the metal. So metal, it is a very tedious, metal to metal, then how can you separate it? That is a bigger challenge for metal supports. But polymer supports, maybe you can break away or soluble kind of a supports which can be dissolved in a solvent. So, but you have to take a special care, extra care in your design for additive manufacturing. Support structure is the crucial part which is going to play. And again, you can, depends on you may have some separation between the part and the platform we need to give, or some kind of the what you call down facing regions where we need to give the support here, or even you have some somewhere overhang portion here, and you have some internal portion which it requires support, and you have some article for in order to give part stability, otherwise it may fall. So without support, so just simply if you give the support here, it won't have sufficient strength, but it may fall. Then we need to give some kind of a support like this, and some isolation island kind of a supports like this we need to give. And supports can be good. Supports can be good for some cases. Say for example, you have some curling effect here. So in order to minimize or this curling effect, you provide some support here. So you have layer 1, 2, 3, 4, 5, 6, so on and so forth. But you can see some peeling or a kind of deformation, a curling effect here. So in order to minimize that curling effect, you add some support here. So support is good here, right? So it's a good. It's not bad here. It's a good here. So and then next part is the slicing. Of course, the slicing again, slicing will be done uniform slicing as far as any proprietary software is concerned. But you can do your research to develop an adaptive slice or a region based slice or an artificial intelligence you can add in that slicing engine, right? So you can think, and so for whatever I am giving a simple calculation, any proprietary software will follow. No, don't see this subject or this is like a rocket science. It is not a rocket science. It is a simple mathematic calculation for the slicing. So it is a simple vector geometry. It's simple vector geometry. How to get your slice point? It is intersection point between you have a STL file and you have a slicing plane, right? So the intersection point of your slice plane with the line or the edge of a triangle, that is STL file. So that is your simple calculation for your slice points. But how to get the number of slices, and of course how to get the number of slices, what is the Z height, maximum Z height of your component minus minimum Z height of the component divided by what is the layer thickness. So if you divide the layer thickness with the maximum Z height to minimum Z height, that will give you the number of slices. And each slice, so you have an increment of layer thickness, and first you take as a reference 0, 0, 0, and then now you increment. So that's what Zi is the for an instant layer. So this is Zi, right? And your slice point is just a simple calculation from the vector. So as you know that this is a three-dimensional model. You have three-dimensional what you call triangle. Each triangle you have a vertex. Each vertex it has a three-dimensional coordinate. That's what I'm talking about. So then we can calculate a simple vector geometry. So then you can get your slicing, and this slicing is normally a uniform slicing. So then once you have done the slicing, so then what next? So we need to generate a G code, or we need to generate a contour data, or we need to generate basically a polyline data. This is 2D printing, but you are at a time you are printing only on the plane, that is a 2D only, or 2.5D with a uniform layer thickness, that is 2.5D. Each layer is a 2.5D. So you generate your tool path or a movement of xy, the coordinate of xy of your polyline. So that's your, so the challenge, or here what we need to do, so you have some internal contours or external contours. How to identify which is internal and which is external? You have a hint, that is in terms of normal. You have a normal. If normal is facing outside, so then you can say that is outside the sub, and if it is inside, so that may be the internal feature. So just you can identify with that thumb rule whether it is an internal contour or external contour. And you may have parent to child relation. So then we need to organize this data, right? And whatever I'm telling is a direct or adaptive slicing. You can try as a research topic. So, but all the proprietary software or open source softwares, it works with the uniform slicing. Means once you set 0.1 mm layer thickness, it is 0.1 mm for first layer as well as last nth layer. You cannot vary in between. But again, freshly you put 0.2, so it is from first layer to last layer, it is 0.2 mm. But you cannot vary. Some layers I need 0.1, some layers I need 0.2. You can write a open GL code or C++ code or whatever you are good in that software. So you can write you can generate some slicing algorithm which it can be directly taken from a CAD software. Why you want to convert as STL? Let it read from the .prt or .part. So then you can, from the direct CAD to the G code, you bypass STL. You can save a lot of data error. You can bypass the errors. Why? Because STL is not 100% complete representation. It's a mesh. Okay, so then you can direct, adaptive, and you have plenty of criterions in the how to fix your how to calculate your layer thickness. If it is uniform, it's okay, but I'm varying. Then how to calculate my layer thickness? So you have different criterions in the literature you can go through, and selective hatching strategies. So then once you have done your slicing part, and then which we need to what you call, generate the tool paths or the laser paths or the what you call the G code, whatever you're talking, G code or tool path. So which we need to generate from that contour data, right? So whatever I discussed here, so you have an STL file and you have the slicing plane. So this is the intersection point, so-called the slice point. You have 1, 2, 3 like this. Say, for example, you have started here, this one, and here, this one, and here, this one. Like at that plane, so how many slice points you have? So you have only two options, right? Either you can go with the clockwise or anti-clockwise. So again, you have normal is the key here, right? So then you can fix whether it is a clockwise or a anti-clockwise. For internal, you have one sense of thing, and for external surface, you have other notation. So then follow the notation, follow the rules, and then so this is what I'm talking about. Say you take a particular slice, so you may have a different levels if you put it in a tree like structure. So you have a model as such, means how many features you have, and one feature may be the father and you have a child, and this child may be other child. You have different generations, right? You have that kind of a structure. So you have a parent child kind of relation, and then you organize all these contours in such a way that, and then you generate a G code or .cli I'm calling. So, and again, the worst part here is you don't have a standardized data format. Like you have STL as for the mesh file is a standard, but there is no standard file like G code. G code is only for maybe the FDM machine, and now it is open source. Now it is G code. Earlier, so you have a company like Stratasys, they have their own file format, and you have 3D systems, they have their own format. You have Z Corp machine, they have their own format. So that's what AICTE has came into picture to standardize, but they are putting their efforts. But still, you have definitely you may have some obstacles, maybe proprietariness. It may be the reason which it may not be allowing them, or maybe some other reasons, right? So anyway, so then you may have a different contour data. I'm talking about the G code, a similar G code. You call as a dot CLI, that's a common layer interface, or dot SLI. Nowadays, you have IPs in step also for 3D printing. But the problem with the IGS or a step, it is very lengthy file. It's a very the size or of course it is lengthy. Why? Because it is a complete data, right? Step or IGS is a design complete data, and step is a total product data. So it may have material information, it may have geometrical, it may have tolerance, it may have manufacturing, this one surface finish tolerance, but it is very lengthy. But anyway, you as of now the contour data may be specific to the machine and specific to the vendor. And then you may look at one more aspect of design for additive manufacturing. Sometimes you may omit your feature. Say this is uniform slicing. Say first layer, second layer, third layer, fourth layer. So my slice thickness is, say, for example, 0.1 mm is my slice thickness. But whereas, which you can see, so this is my 0.1 mm layer thickness, but from here to here it may be 0.05 mm. So in that case you have omitted this curve, yes or no? And here also, and here also, here also. So these are called as the peak features. So you may lose your peak features because of the constraint of layer thickness, the feature which is less than your layer thickness of height, and then obviously you may lose your feature. So then the idea here is you can adaptively slice wherever you have some expert system or artificial intelligence. So then it should, so all these slicing algorithms are also a bit of intelligence, right? Otherwise intelligent in terms of mathematics maybe. So then you need to um, subdivide rather than you reduce the layer thickness wherever you have a critical features or a peak features. Your algorithm first it has to scan and identify wherever you have some peak features, and further you reduce the layer thickness. You have reduced layer thickness here. You don't have a peak features, so you can put very thicker layer like this. So like this you can adaptively vary the layer thickness. And last one is a toolpath generation. So toolpath is exactly how your FDM head has to deposit the material or your laser has to scan. How to do that? So any 3D printing system, first it will lay the outer layer, the boundary, and once you put the boundary and you fill that boundary, you can use any tool path strategy. So then why the tool path strategy is important? Definitely there is importance. It is judging your strength, it is judging your accuracy, mechanical strength. If it is more denser or if you overlap, definitely you may have very good melting or very good bonding between the powder particles or maybe the fusing of the polymer. So definitely it is judging your strength, not only strength, accuracy, and of course build time. So if you have a more dense overlapped one, it may take longer time, right? So anyway, how to fill your boundary. So you may go with simply horizontal vertical, combination of horizontal vertical, or some, you can some inclination. You can have the raster 45 degrees, or you can vary from 0 to 90 degrees your raster angle, right? And it may be combination of contour, raster, raster contour, or things like that. So you can have a tool path can move or can have any pattern. The pattern is judging your quality. So this is about, and topological optimization is also part of design for additive manufacturing. So what do you mean by topological optimization? You know design optimization, right? So you know the design optimization. We optimize the weight, and we work FEM, the finite mesh analysis to optimize your designs. But what is topological optimization? What do you mean by that? Say I have the same part I'm using for my the previous lecture also. Why? Because it has impressed me a lot. So this is from Arup. There is a one construction company in Netherlands, Switzerland. So they have recently, this was the traditional design for some cabling or some construction. There you can see there are some holes here, and which the cables will be, put here, and then this is for a structure, so where it will go, and then where your cables will be fixed here. It has to take all that loads, and traditionally it may be machined, or which you can see some welding also on this. And then what they realized, so they have redesigned it, so which we can see, this is the topologically optimized, means lightweighting. Otherwise you can put it another way, you are optimizing the weight, or you're reducing the weight, not optimizing, you're reducing the weight without hampering the functionality. Sometimes the stiffness may be more also if you compare with this to this, or sometimes at least with the intention, without compromising the functionality with the traditional design, and you are able to get the double benefit here. You are reducing the weight and cost of production also. And this is the one version, and recently they made one more version which is further reduce the weight. So from here to here, 60 to 70% reduction of the weight, and without affecting the functionality of with the original design. And of course improved stiffness, durability 10 to 20% at least, and reducing the cost probably. So then that is the, so you might have designed this in a software, but designing is not the goal, fabrication is your goal, right? So then I can show several designs in the computer, but at the end of the day I have to fabricate. So your traditional conventional manufacturing practices cannot allow you to make, or it may allow you to make, but the cost of production may be more. But if you are compromised with this, okay, you can go with, so that's about your mindset and the application demands. So anyway, so and there is a bit of I took this case study from the Arup. Actually they have done the Van Mises stress analysis, which we can see, this is a traditional design, of course, and which you can see the red ones are the more stressed areas, and from here to here there is no much improvement, but which we can see almost your red parts are almost disappeared. So the stress concentration is very low here if you compare from traditional design and the version 1 and the version 2. And this is the real application where the cables will be fitting here. As I mentioned, you have that holes now, so without compromising your functionality. So then it has designed and it has simulated, and it has proved also by fixing this for the real time application where you can see these cables are attached to this holes through this bolts and nuts. So just a recap, the design procedure or the CAD modeling scenario. You have a parametric design, right, where you can vary one parameter and then entire design accordingly. So you have some knuckle joint. If you vary the shaft of a knuckle joint, so other design will getting changed as for the proportionally. So then you have a parametric design, of course, and recently you have a generative design, and there is a slight difference between the generative design and topologically optimized designs. So the generative design is something like consolidating the parts. Say I have 20 parts, so I may consolidate 20 into a single part. That may be the generative design, but topological optimization is quite contrast. So you are removing the material rather than, which you can see. So this is the original design, and topologically you are means you are removing the material wherever it doesn't require at all. So without compromising the functionality. So you are keep on removing the material and you are making a lightweight. So that is called a topologically optimized one. And nowadays lattice structures are bionic designs, bio-inspired designs, right? So you have some softwares like N-topology or altered solid thinking, and you have Fractum, and even from the Autodesk you can do a bit of this kind of generative designs here from the Autodesk. And then you have exclusively for topological optimization, you have a good software, something like this, which you can see. And then this is what I'm talking about. The generative design, probably it may consolidate the parts. Say I have 8 parts, so I made 8 parts. This is an automobile case study, which this is an what you call your seat, the which the seat support or the seat frame. So this was the traditional design where you used to have 8 components, but through generative design they could able to redesign with a single part. So this is a generative design, and this is a topologically optimized. And of course lattice structures and bionic structures, which even in the first class we have discussed, like heat exchanger and other stuff, where you have a lattice structure and you have a bionic organically inspired, or the cell from the biology the designer might have inspired. And to name a few topological optimized softwares like Alter, OptiStruct, and you have other softwares under this topological optimization domain. And of course build simulation softwares. The build simulation softwares, why you want to simulate the builds? Of course you do you normally do for the traditional manufacturing practice also. Like you take a CNC machine, definitely will check the tool path verification. We will be doing it before going for the actual machining. And here also, even for the support generation, or even for the residual stresses, or any distortion it is coming, or even any, if it is a powder bed system, the recoater may be damaging your part, so it may be clashing, or there may be some collision of your recoater to the already made layers, so it may damage your part. So that is the, and if your scraper is not having strength, the scraper itself, it may break. So then build failures or may happen. So of course you need to simulate better, and you have the simulation software like 3D Expert from 3D Systems. So then you can simulate, you can have a minimum risk of printer damages or minimum number of build trials. Otherwise we need to, basically it's a trial and error kind of practice. So then instead of going for a trial and error, so not only during build, even for the post processing also you can simulate. So what kind of heat treatment we are going to use, and what kind of hip or a support removal, and then you have a multi-physics, multi-scale modeling, right? So to name a few, so you have ANSYS multi-physics exclusively for additive, that is additive print. And from the 3D systems, the previous image, that is 3D expert software. And you have a Geonics from Virfac and ESI, and there is a software called additive manufacturing, and Alpha Star, and this Geo 3DP, and Extreme Dizimat. Dizimat is for only polymers, but majority of this simulation is for metal. Metal is costly, that's what people are investing or developing metal simulation software rather than polymer simulation. So but Dizimat is a polymer simulation software. And additive works, you have, from the additive works you have Amphony, on from Hexagon you have a Simufact additive, and Autodesk you have a NetFab, and from Siemens you have a NX Sim Center, simulation center. So this is some of the simulation softwares were available in the market. So then the last part is quality check. So how do you check quality and how do you test it? And standards will come into picture, right? But this technology is not a mature technology. You cannot find much of the standards from ASTM or any other standard, DIN standards from German or Indian standards or German standards or ISO standards. But ISO, ASCII and ASM, they are working together to come out with some standards. But Professor Krishnanand is going to talk exclusively on that standards part during last lecture, that is 14th session. But I will give some glimpse, but not on the standards. At least standards and testing both are related. So, and of course testing and quality testing or quality control or a process control, in situ control. So then right from the beginning we need to test the quality. Here, say for example, you take your raw material, maybe powder or maybe filament. So we need to test the quality, whether it is up to the mark, up to the standards. Your filament is 1.75 diameter or 3 mm diameter, or the powder particle size is 20 micron, 30 micron or 40 micron, whether it's flowable, are you able to flow the material, are you able to spread the material, are you able to melt the material. So we need to check right from the starting of the material. We need to specify, and sometimes we need, or every time we need to check them, any moisture is there in the material or whether the airflow will be good. This is before the start process, means during the raw material processing or feeding the raw material to the machine. But what about during the printing? So during the printing, so then we need to have parameters like laser power, and you have a nozzle monitoring system and temperature monitoring system. Of course, you have some what you call, all these parameters can be monitored, and then in situ kind of monitoring system. You use some sensors and use some cameras, high-speed cameras, no, to check. Say for example, for metal 3D printers, so you have a melt pool. So then what is the melt pool temperature and what is the size of a melt pool? What is the heat map, right? So all these things. So monitoring is one part. Another one is how to correct. But as of now, but still this monitoring and correction during, that is in situ, still in the initial stage, very beginning, we can put it in that way. So then how do you test or how do you monitor your dimensional accuracy? How do you monitor your surface finish? So maybe the measurement, or maybe after the post processing. So here as built and after post processing, right? So it will, your accuracy and surface finish will change. And post-processing material quality, like you have, somebody was asking yesterday a lot of questions on the testing. Then I intentionally put these some of the slides here. So you have a non-destructive testing or a destructive testing to do this kind of quality testing, right? So this is what in each and every, right from the raw material to the testing before application, right? Just before the application. So then you will be testing for the quality. So of course, in the literature, you may find some limited softwares or limited services is available to test. So which we can see, I took this from one of the literature, and still you can see under development, all are under development. Say for example, closed loop control. So you don't have right now a closed loop controller from the, when can you say it's a closed loop controller? So we need to correct if something goes wrong, your melt pool is reducing the size, and then we need to increase the laser power or something we need to do, right? Until unless you doesn't have a closed loop controller, you cannot. So then you may, one level is you may identify, but how to correct? So then still it is under development. Then people are looking to put some kind of a closed loop controller, and maybe during printing, during melting, some kind of a metallurgical data, like what is the melt pool and the maps, the heat maps, right? And in process quality data, and then you have a post processing test data, or even it can be a kind of, no, you have nowadays big data analysis, right? So big data analysis is going to play a vital role here. So we need to do a big data analysis, and product lifecycle management and workflow optimization. Of course, like Siemens, they have some kind of a PLM solutions, as we know that. So still for the 3D printing, so then it should be adopted, maybe evaluate, purchase, product, analyze. So of course you have some Link 3D and other softwares. Slowly now it's coming up. And of course, artificial intelligence is going to be play a vital role in 3D printing or additive manufacturing to enhance. So you may be incorporating a machine vision system and artificial intelligence. So which you can see there is a multi-material inkjet printing. So which you have a digital print recorded for each layer. Say you can record each layer, the history of each layer, and then you can compare or you can superimpose, and then any deviation, right? So you can develop a kind of machine learning algorithms to do this. And you have a voxel level based real-time feedback controller. So that's what, like you have a huge scope to work with these kind of controllers, feedback controllers. So once you have a recorded data for each layer, the history, it got saved, and you superimpose every time. And if there is any deviation, so your algorithm has to do such kind of corrections. So there is a huge scope to research, right? Some companies like Markforged, Blacksmith, so they are coming with some kind of, but it is very beginning. So somebody wants to do some research or file some patent. So this is a good area to work. And even you can integrate your artificial intelligence, big data analysis, of course, blockchain for the security. Yeah, of course, we have some data security. That's what I'm talking. So data security is a major issue. Why? Because this is a digital cloud based. Nowadays we are working on a cloud based systems, right? So security, data security, cyber security, right? And virtual labs or virtual facility. So I have a physical facility. So then companies like SM Bricks, so then you can rent a virtual printer, literally. and then you can do simulation, or you can, right? And say recently Boeing has collaborated with this Assembrix on the security of the 3D printing, and same thing from the GE. So they are working for the blockchains for the 3D printing securities, verification, validation. And then you have the virtual secure manufacturing space, so where your software to manage and protect the IPs, and they may be sharing with the vendor these designs and manufacturing. So then we need to protect, then there will be a double extra care should be taken if you are sharing your data, right? You are sharing the data to the vendor, right? So then how to secure your data? You have a kind of, you can enable secured and more efficient production process, and you can rent a virtual printer literally from these sources. And then material testing. So what you do, the material testing. So material testing is, you have a NDT and DT, that is non-destructive and destructive testing methods, and you're testing of right from the starting of the material, which I already given some hint, like powder testing, like how it will be poured, will be flow and particle size, any contaminants and any moisture it contains in the plastic raw material, and in situ melt pool monitoring and heat mapping. And you may use some kind of light beam here to do that, for monitoring the melt pool. And you may use some ultrasound and eddy current kind of tools, non-destructive tools like X-ray, CT, penetration dye testing. Normally you do for the surface cracks, and then you do a process compensated resonance testing, and then you have, of course, a destructive testing methods for fatigue, toughness, shear, and tensile strength. And last slide is talking about where can you find these 3D printing services. So you can find the 3D printing services from 3D systems, and you have a 3D hubs, forecast, critique, and you have a 3D experience, and you have proto labs, of course, stratasys, I materialize, shape waves. These are the places where you can get 3D printing surfaces, the services. And whereas shape waves, you can customize the objects also here. And 3D hubs, 3D systems, on demand, I materialize, proto labs, and stratasys. These are the well-known 3D printing services across the globe. I'm talking about across the globe. Yeah, and then where can you find your resources? A lot of people are asking, sir, I need that, this. So you can go and visit these websites. You can find a lot of stuff like all 3D printing, metal AM, Waller's report, 3D metal printing, 3D printing, 3D printing industry. So you have several forums, news or information, you can get it. And of course, some conferences. Formnext is the biggest conference in the European country. And of course, FFF from US, Texas University, there is a big conference every year they will conduct. So like that, you can find several conferences. So I think I have taken much time than the schedule, but so I'm stopping here. Then we will open up for the questions.
Thank you,
Rakesh.
sir. Yeah, yes. Very informative talk, sir. Thank you very much. And participants, if you have any doubt or questions, you may ask. In the chat box, one person is asking, sir, 182. Yeah, yeah, he may ask. You can unmute him.
So please, we'll allow the next speaker also to talk and be. So I will be available. Even you can ask afterwards also. Why? Because we are touching 12 o'clock. So other speaker may be in line. Okay, then maybe 4 or 5 questions we can take. Yes.
Hello.
Yes.
Sir, as you talk regarding surface roughness of the 3D printed parts, like conventional machining, we have some surface finishing operations. So do we have some facility of 3D printed part to improve the surface roughness, some chemical or some other
Of course.
treatments? So
Of course, we can chemically treat whatever conventional the super finishing process. We can apply all that. Yes.
okay,
Next.
okay.
Can I have a question? Can
Yes,
I have a
please.
question, sir? I'm Aditya from CBIT. Sir,
Yes.
we're talking about design for additive manufacturing. Sir, what is the case when can you throw a light in the case where a part is partly partly damaged, and instead of replacing the entire part, can we design that particular part and make sure that the part is strong, that it's bonded properly?
Of course.
Like,
Yeah, it
say,
is possible. Yeah,
okay,
understood. I understood your question. It's
sorry, one
possible.
more.
Hmm.
Okay, sir. One more question, sir. While talking about bone modeling, sir, is it possible for by polymer 3D printing like FDM to produce the porosities required as mimical to the human bone?
Of course. I will come to the first question. That is, we are talking about the repair of the part, right? So yes.
Yes,
So
sir. Yes, sir.
repairing of the part or refurbishing of the part is very much done with the additive manufacturing processes like DED and even with the some kind of powder bed process also it is possible. DED is the right one, but we must have a CAD software and you reverse engineer it and you superimpose this with the original data and you will get the deviation. So like that you can absolutely get match 100% or at least 99% you can match with the original geometry with the repaired after this one service parts also we can do. You can regain the original size, shape and the geometry. And second question is about the bone modeling. Yes. So any FDM process, as I already mentioned, it is not the magic of software, hardware. It's the magic of software. So whatever the bone design you have done in your software, it's going to replicate. But maybe here and there your technology varying on your laser technology, it may give more precise than FDM. But that's only the thing. But almost you
So
can.
yes,
Yeah.
sir. Codes are will micrometers. No, sir. Is it possible using
Yes.
FDM? Because I
No,
want to make a polymer composite, sir.
no. It's not possible with FDM. You have to shift to SLA or any other precise
Okay.
prints. Yeah. Next.
Okay. Okay, sir. Thank
Is
you,
it
sir.
clear? Yeah.
Thank you, sir. Thanks a lot, sir.
Sir, one more question. From Mohit Gupta, what is the use of
Topological optimization.
topological optimization, where it is used with
Yeah.
respect to medical printing, where it is used?
Yeah. All these bones, if you see the inside the bone, spongy bone, that is only the porous one. That is exactly the lattice structure. It is also part of the topological optimization. But exactly speaking, aerospace is the right industry using the topological optimization where your weight is the criteria, payload is the criteria. So if you could save, if you could reduce 1 kg of your payload, you could save 500 to 600 kg of fuel per year, roughly. So you can use it for the aerospace, automobile also same logic applies for the mileage. So you can use these areas wherever you need weight constraint. So topological optimization is the best solution for that. Yes. Next question. I think
One
I have
more
cleared. The last question, probably.
repository SQL file can be reworked.
What is that?
A repository SQL file can be reworked.
Can he elaborate? Who is that? No, I'm not getting the question. What repository?
Actually, he's asking from the repository, like from the data
Open source.
we got
Open
the
source.
HTML can be
Right.
reworked.
Rework. Yeah, we can rework. We are going to have some exercise also on that. Srikanth is going to show you some of the models can be downloaded from the repository and it can be imported to your SolidWorks or any other software to do customization or to modification. Yes, it is possible.
And one more thing, sir. Kanchi Sai Prasad Naidu.
There's the last
Sir,
question.
yeah, this is the last question, participant. Sir, could you please brief a bit more about customized algorithms for adaptive slicing? Like he is asking more about the adaptive slicing.
That is absolutely your mathematical modeling you have to do. Like, so you have to first go and study the literature, conventional marching algorithm for the conventional uniform slicing algorithm. Basically, it's a marching algorithm. You search Google search, you will get a marching algorithm. First, you understand what is that marching algorithm. So marching algorithm is for only the uniform slicing, but whereas you have to write your code for as for the adaptation of, but you have to create your own interface to the machine for your algorithm. The existing proprietary machines won't work for the adaptive slicing. You have to create your own interface to the machine. But everything, it is all about the mathematics or the mathematical modeling and vector calculation. You have to work on the STL if it is STL, or if it is a CAD model directly you are using it. So you have to manipulate your NURBS file, or if it is a B-spline, so you have to write an algorithm to identify that curve, or that if it is a NURBS curve, it's a NURBS mathematics which should be involved. And if it is STL and it is a simple, that is only the straight line or the edge of a triangle. So the mathematics involved is easier. But if you want to write a adaptive, so definitely we need to rewrite the existing rules, and definitely we have a several criterions. You can even further divide your thing into region based, region wise you can further divide.
Yeah.
Yes.
Sir, thank you,
Yes.
sir. Sir, one more thing. We have quiz question. Quiz check.
Yes. Yeah, go ahead. So, yeah, go ahead. I'm handing over to you, Rakesh.
Yes.
Thank you. Thank you.
Yes, sir.
You can attempt.
The participants, the quiz question link is pasted in the chat box. Please go through that. The Google form is activated, and it will be deactivated after 10 minutes. Just go fast and then attempt it.
Hello, sir. Hello, sir. In that Google quiz, I'm not able to click on any option today. I don't know why. If I'm selecting, I'm not able to click on any option.